Hello, welcome to this video introducing continuity. So what does it mean for a function to be continuous? We'll look at that. My name is Nakia. Thank you for watching. Let's get started. A function is continuous at a point x equals a if the following is true. If we have the limit as x goes towards a from the left equal to the limit as x goes towards a from the right, that's saying that the limit exists, and at the same time, it's equal to the actual function value if you were to plug a in. Two parts there. The limit exists, and it's equal to the function value. We've seen where the limit exists, but it's not the function value. We've seen that there's these kinds of functions that have a hole in the graph. They would not be continuous at that particular x value. So we need them to be headed to the same place, and we need the function to be there to have continuity at a point. All right, so the left-hand part here is that the limit exists, and the right-hand part says basically that the function value is equal to that limit value. All right, great. Here's a graph where we have the action going on. We have the function headed towards f of a, and there's a dot. Like there's no hole there. The actual function is there. Whether the dot is there or not, I mean, like you can just, if you just had a graph, you would assume then that the function value is there. And so the function approaches f of a, and the value is actually f of a. That's what it means to be continuous at a point. For us, at least. Okay. All right, great. So what's the opposite of that? What does it mean to be discontinuous at a point? We'll have three different types. Okay. The first type is going to be what we've seen before, where, yeah, your left hand and your right hand are agreeing with each other, but the function value is not there. Or maybe the function value has been removed. Maybe the function value is not there at all. The point is that this type of discontinuity is where the left hand and the right hand agree, but the function value isn't equal to that limit value. That's called a removable discontinuity. The point should be there, but it's been removed. That's the category of removable discontinuity. First category. Now, second category is when you have the function from the left hand, the limit is actually someplace else than what's going on from the right hand. The limit from the left is not equal to the limit from the right. This particular type of function is called the greatest integer function. And so if the number is 1.5 inside of there, the greatest integer less than or equal to 1.5 is the output value, which is 1. This is commonly called the taxi cab function because in a taxi cab, they still exist. What you have is the fare is stuck on a certain value for a certain amount of time or a certain amount of distance traveled, and then it jumps to a new value. Stays on that for a little while, and then it jumps again. And so that's what's going on here. At x equals 1, say, the function on the left-hand side is headed towards 0. The function on the right-hand side is headed towards 1. The actual function value is 1. They don't agree. You've had what's called a jump discontinuity. The function is jumped. Left-hand limit doesn't equal right-hand limit. Maybe one of them, like the right-hand limit, equals to the function value, but now, this particular function, remember, is called the greatest integer function, in case it comes up again. You basically are chopping off all decimal parts. If you have 1.999 and you plug it into this function, it's like a square bracket with a double bar, it comes out as a 1. Okay, so you chop off the decimal part and you just have the whole number part. Okay, it's the greatest integer less than or equal to the number. That's what it's called, greatest integer function, just so you know. Okay, all right, great. And then the final type of discontinuity is when you have an infinite discontinuity. Your function goes off to infinity. Both together, one goes to infinity, one goes to negative infinity, one goes, it doesn't matter. As soon as one of those left hand or right hand limits are infinite, that's an infinite discontinuity. Okay, all right, great. Those are our three categories of what it means for a function to not be continuous, and how it manifests itself in the graph. Okay. All right. Let's look at an example then. of what one-sided continuity looks like for these types of functions. You know, we have one-side limits, right? So one-side continuity could be a concept that we could talk about. You could be continuous from only one side. Like if your left-hand limit is headed to some value and the function value is there, like in a taxi cab problem, then that's continuity, but it's only from that one side, not from the other side. And so if the limit as x goes to a from the left-hand side is equal to the actual function value, if from the left you are headed to where the function is at, that's one-sided continuity, continuous from the left. Or from the right. This is what happened with the taxi cab function. Where your function was headed to on the right-hand side was where the function was at. On the left-hand side, it was headed someplace else. And so the limit as x goes to a from the right is equal to the function value. That's one-sided continuity. So this particular function here, the graph of it manifests this type of one-sided continuity. Let's look at where this function is discontinuous at. Let's go from left to right. First place this function discontinuous, the smallest x value where this function is discontinuous at is at -4. Okay, what type of discontinuity is that? Removable. Left hand equals right hand, function not there. Next value where f is discontinuous at, -2. It's a jump. You're headed to one place, and then you jump down the other side. You're headed someplace else totally different. Jump discontinuity at -2. Don't be deceived. X equals 0 is not a discontinuity. The function is headed to that point, then it goes off to the continues on, and there's no indication that the function value isn't there. We'll call that something else later when we learn derivatives. That's a place where you can't take the derivative at, but that is a place where the function is continuous at. Okay, so then we move to x equals 2, another jump, and then x equals 4, which is an infinite discontinuity. That's meant to, like when the function goes off like that and there's no arrow, it's meant to seem like it's going up. That's what it means. It's going off to infinity, negative infinity there. So these are all discontinuities, right? The function is discontinuous at these x values. But you can recover one-sided continuity at some of these x values. Not at -4 though. No way to recover one-sided continuity. The left and right are headed to the same place, but they're not equal to the function value. At -2 though, you're from the left, you're headed to the function value. From the right, you're not. So at -2, you're able to recover one-sided continuity from the left. Okay, that's the only place on here where you have left-hand continuity at a discontinuity, a point where the function is discontinuous at. Okay, and then on at 2 and at 4, where you're headed from the right-hand side is where you're at. They indicate that by the dot there. So at 2 and at 4, we have the ability to recover at least one-sided continuity. Okay. All right, great. So we in this video, we've looked at the definition of what it means to be continuous at a point. And we looked at one-sided continuity. And we looked at a couple examples and categorized the types of discontinuities. Let's go ahead and end this video now. Come back with another video where we look at what does it mean for a function to be continuous on an entire interval of points? How do you look at a function and just know where it's continuous at? That'll be in the next video. Thank you for watching. My name is Nakia. I'll see you in the next video. Take care.